we're going to do this lab 7, and it's going to be another exercise in spatial interpolation. But this time we're going to use, instead of spatial analyst, we're going to use geostatistical analyst, so we can kind of explore kriging a little bit further. I'm going to show you that you can still do IDW interpolation in geostatistical analyst, but we'll look at a few of the options, and there's some questions to answer at the end of the lab. So, on the coast, can you all hear me? Okay, good. All right, I have the video going. You need to refer to that. So what I did was I went to the labs page and I hit exercise 7, and I'm going to save that data set. I'm using Firefox today. I don't know why, instead of Chrome, but so I saved it, and I don't know why this keeps coming up. I saved it, and I saved it 8 times, I guess. I'm going to open it and take the data and save it on my local computer somewhere. I'm going to just put it in ctemp lab 7. Should be there. Save it there. Looks like it didn't save it. I'll just take this. Oops. Let's see, temp, and copy it over there. There we go, lab 7. So I've got my lab 7. I'm going to open up the document. You can read through it. There's not a whole lot of information there. It gives you a little bit of an introductory and refers you back to the lecture notes and to the reading. So what we're going to do is use geostatistical analysts to explore some data, and this is precipitation data for the United States. That's what we're looking at. So it's average yearly temperatures for the United States, and I've got that up. So I'm going to go ahead and start by opening up ArcMap. Should have done that before. And this first screenshot is actually from the older versions, and it's not that's not the data set we're going to use, but the later screenshots are from the newer versions of the software. So go ahead and add in the U.S. Actually, go ahead and add in everything, and you can just turn off for now everything except for the U.S. I said PowerPoint. So when you see PPT, sometimes that's the file extension for the PowerPoint stations. No, the precipitation at the yearly precipitation at these weather locations. In fact, we're going to be using precipitation as the example as we work through the lab, but then at the very end, I actually have you also look at temperature. So both of that information is in there. So we've got 5 fields. We've got the latitude and longitude, and those were actually imported along with the data set. So the original data set wasn't a shape file. It was just a text file that had the latitude, the longitude of all the weather stations. It also had some other information that I didn't import, like the name of the weather station and so on. And then the average yearly precipitation and the average yearly temperature there. Okay. Now, I'm not sure if it's the average min or the average max. It's probably one of those two. But the temperature is definitely in Celsius, not in Fahrenheit, obviously. For example, just up the road here, it looks like it's somewhere in northern Mississippi or Alabama. The temperature is not 16.6. That'd be really cold. All right, so clear that out. Oops. Selection, clear selected features. I'm going to center this a little better. Actually, we don't even need this. The first thing that I want to do that we didn't cover in class last time when we brought up geostatistical analyst is to show you that you can explore your data by looking at a few of these different ways to kind of look at your data. The only one I explicitly talk about in the lab is this one, the covariance, semi-variance covariance cloud. But like we could, for example, we could also look at the trend, and it's not very high resolution data set, but we could use this a data set like this to kind of look at three-dimensionally the trend of. We got to make sure that we're turning on the right layer. We're looking at latitude right now, which might actually be kind of interesting to start with. So if I look at this from this angle, why does it appear that we're going upwards from south to north? And it almost looks like an exact linear trend. As you travel north, remember the variable we're mapping is latitude. As you travel north, that variable latitude is increasing. Should we expect that? So it's not really interesting to look at, but it's basically proving that that our GIS is doing what it should. So if we change this to longitude, we would expect as we rotated this back around, so the longitude is decreasing as we move. It's hard to tell, but like, you know, this is the eastern seaboard. That's Florida. Let's just zoom in back and forth. I don't know why this is disabled, but it's disabled to kind of tilt it up. But you can see as we move from east to west, we get decreasing. Why is it decreasing? It's becoming more negative. Remember that usually the way that we express latitude and longitude is to use negative numbers for the Western Hemisphere, which we live in the Western Hemisphere. So no more negative values. Well, the variable that we're really interested in looking at is yearly precipitation. So you can see that. And now if you look, it still makes sense to us. You know, we're familiar with the United States. And we can see that in the east we get a lot more precipitation, and then out west a lot not as much. And look, right up here in the Pacific Northwest you get another spike. Okay? And I can tell that's the Pacific Northwest because as I rotate back around there, you can see in the Southwest, even coastal Southwest, like where I'm from, my neck of the woods, it's still fairly dry. Yeah, of course, right on the coast, you get a little bit more rain than you do inland. You know, Southern California, coastal Southern California gets more rain than Palm Springs and the Arizona area, but not much more. I think when I was a kid, I don't think the Dodgers ever got rained out. So we're looking at the trend surface map, which is not something that I included in the lab, but you can see that maybe. Yeah. It'd be nice if that was a little more interactive. But the one they pointed out in the lab is you can explore your data by looking at the semi-variance covariance cloud, because that's really what we talked about this week. And again, it would be interesting, I think, to start off by, I'm going to unpin this, move this over. I think it'd be interesting to start off by looking at a variable that we can predict. You know, we know that latitude does start here lower and go up as you go in this direction. Okay, and so with this variance covariance cloud, you can highlight things, and it will show you all the pairs, because what it's doing when it's making this cloud is taking all of the pairs of all of the data and plotting them on the map according to their distance. So distance is this axis, and then the semivariance between the pairs is in this direction, okay? And then we can actually highlight an individual pair, okay? And it's hard to see that these are pairs, but if we zoom in, we can see that's a pair. And we can see that these are pairs. So these pairs are very low in distance and in semivariance. In other words, they have a very similar latitude and a very small distance between them. And if we look, see if I can, I don't know if I can pick just one. Yeah, that's just one. My guess is that one. So that's very low, very low variance. Now, as we go up here, we start getting more and more pairs. Okay. More and more pairs. These pairs have a very varying distance. So now we're going from, you know, this isn't a straight up distance. Okay? It's a distance applied to some function that's increasing at a constant rate. So let's look way over here. Okay. What would this pair mean? This pair would mean that we had a very high distance away from each other, and also a very large variance. In other words, there's a very big difference between the latitude values. So we'd expect these points to be far away in latitude and far away from each other. If you look at that, those are about as far away in distance as you can get, and also be high in latitude. Now, if we move to this one right here, actually, let's move to this one right there, because that one's almost the same distance away, but the latitude value is much more similar. My guess is it's one of those ones in Southern California, or we're getting closer to Southern California. I guess if we moved all the way down here in the same X direction, we would get to a point. It's picking a different pair now. It's no longer, but these pairs are very far away from each other, but they have a very similar value. So as you move this way on the y-axis, as you move down, you find things that are more and more similar to each other, even though they're, in this case, far away from each other. So maybe the best way to think about this is if we divided this chart up into 4 quadrants, okay, these would generally be things that are closer and things that are more the same in this quadrant. In this quadrant, these would be things that are closer but different. These would be things that are, these are the things that are further away and different, and these are things that are further away and similar. Okay. All right, so let's change this to another variable, and that is precipitation. So we change this to precipitation, and let's clear out the selection, clear selected features. Okay. All right. If you remember this area right here, what was this quadrant? What was this quadrant right here? What did that represent? Things that are, in terms of distance, are those far away or close? Close, relatively close in that quadrant. This quadrant right here. Now, in terms of the variance, okay, it's really semi-variance. We're dividing, all that means is we're multiplying it by 0.5. So in terms of the variance, would those vary a lot or vary a little? Relatively, if they're on that axis. Because remember, this is variance. So things that are in this area, are those similar or dissimilar? Dissimilar, exactly. So let's see what those are. I'm just going to select the ones that are kind of very much in the corner here. If you look at those that are in the corner, okay, what are all those pairs that are dissimilar what do they all have in common? They're close, but relatively close. Okay. We're talking about the whole United States. Those are still relatively close. They're relatively close to one another, but they're very dissimilar. Okay. Can you explain why? I think is this actually the first question? If it's not, then it probably should have been. I think it is the first question, as I remember. Nope, I didn't ask a question on that, but I did. I didn't ask you to turn in a question, but I did ask. So we're right here in the lab. Try to understand why what this information would mean from a geographic perspective. That's what I meant. Okay, so why would these be different? Yeah, exactly. And there is a coastal mountain range, the Cascades, that does that. So, but according to precipitation, remember we looked at that map. Okay, we looked at that map at first. Is the precipitation in the Pacific Northwest much greater than it is out here in? This is basically a desert. Even this area is close to a desert. I don't know if it's specifically defined as that, but this area has not much rainfall every year, and this area has hardly any rainfall. It's where my mom lives in Southern California, Palm Springs, and then into Arizona area here. So that area is really, really dry. And so all these lag distances, which are very similar lag distances, have even though they're relatively low, they have a high covariance. I mean, a high variance, high semivariance. So if we looked out here, okay, these areas, we'd expect them to be not very much related. So these have a long lag distance, okay, long distance, and we're still out here in the west. These areas are so dry that they're always kind of the examples here. So these are very far distances, and compared to some of these areas in the southeast where it rains a lot, there's a very, very big difference. Right? In the lab, I didn't have you do this, but you could go to temperature and see if you could find similar issues. So here's temperature. Okay, temperature. And if we looked, we don't have quite as many, but if we looked up here in this corner again, these are areas that have a relatively high covariance and a relatively low distance between them. So you see some of these differences here, and some of these differences here. I don't know as much about explaining those differences as the precipitation differences, but yeah, altitude is probably has a lot to do with it. This area is fairly high. All these areas are fairly high. These areas are fairly low. The Continental Divide that is down here is one of the lowest points in the Continental Divide. Yeah. That's I think I drive home that way a lot, not a lot, but I drive home to Southern California. I think the highest that you get on the interstate is still less than a mile high. It's in the 4,000 feet area, which if you took this route, which I did sometimes, driving through the middle of the country, I think that on the interstate you get up into even on the interstate you get up well over 10,000 feet. So, and the interstates are trying to choose the small passes. So that very well could be. All right, so let's switch it back to precipitation and clear this out. Selection, clear selected features. All right, so we're right here in the lab. Okay. A little bit before this, first thing that we're going to do is demonstrate that you can do IDW with the geostatistical analyst. So if you close this box completely and go to the wizard here, all you have to do on this screen is make sure that latitude is set for, is changed to precipitation. So you're doing the yearly precipitation. And make sure that this method that you select is inverse distance weighted. Okay, so you click next. And here you have a screen that will allow you to change a lot of those parameters that we talked about last week that you're familiar with. Changes to the minimum neighbors, the maximum neighbors. You could change the search neighborhood type to being standard or smooth, which is actually different. That does not exist on the other method.
Can I go back to step 1?
Sure. So there's only 2 things that you would change from the defaults on this screen. That would be make sure that this is selected, inverse distance weighting, and make sure that the data field is PPT. Almost said PowerPoint again. PPT year. Okay. Then hit next. And then the only thing that we're going to do on this screen is something that also is not available from the spatial analyst toolbox, is that you can optimize your power value. Hit optimize power value, and it'll turn it'll turn out the value. It'll optimize that value. And this is the help on what it's doing. It's basically fitting a curve to the RMSE values as it does its prediction. So it does a prediction, and it holds out some of the values, and then sees if those values are different from how different they are from the curve using different different values for the power. And remember what the power does? Okay, as the power increases, we're weighting closer points higher. As the power increases, closer points get weighted more. So your surface becomes more, less smooth. All right, so that's the only thing we're going to do there. And then we're going to hit next. And it's going to show you the result of the cross-validation. So the cross-validation here is the measured versus the predicted, where it basically performs the interpolation multiple times and holds out that value each time in order to come up with this. Now, the way it does this so quickly is it doesn't perform the interpolation for every single cell value. It doesn't do that. It only performs the interpolation for every single known point while holding out that known point. So it's not, when interpolation happens, if you think about it, what it has to do is perform the interpolation for the center point of every cell. And that's a lot of cells. For example, if your grids were 1,000 by 1,000, it would have to perform that. What's 1,000 times 1,000? You just take the zeros, you knock them together. So 0, 0, 0, 0, 0, 0, 1 in the beginning. That number is 1,000,000. Right? So they have to perform 1,000,000 calculations. That's a lot of calculations for it to perform. But here, if we have, in our case, I don't know exactly how many we have 222 points. It still has to do the interpolation 222 times, because it leaves out 1 each time, and it performs the interpolation 222 times to do that. So that's 222 is a lot different than 1,000,000, and it can do that faster. So when I actually hit finish here, it's still going to do it pretty quickly, but it's going to take a little bit longer than when I hit next the last time. So I hit finish. Oh, Well, it's going to tell me, give me some statistics. I hit OK. And it did it pretty fast. I mean, computers are fast these days. And I don't know if this is 1,000 by 1,000. It might not be that much. So this is our output result of precipitation. Okay, let's look at it. Does it make sense? Yeah, it makes sense. We got higher precipitation values. You know, if I was making this map, I would change the color scheme because the color ramp stinks for precipitation here. Something like maybe like that, or something that goes from a color that looks like dry to a color that looks like wet, at least. So something like this would be the result. Okay, and like I said before, the output to the spatial analyst toolbox that we did last week is always a grid. It's a gridded data set. This is still actually not a grid. It's only in memory. Okay, if I close down ArcMap right now without saving, it would just go away. Okay, it's saved. The process itself is saved, and so it performs that process again once you open up ArcGIS again and shows you the result. Okay. If I want to save this data, I have to go data export to raster. But even though it's saved like this, in fact, because it's saved like this, there's some cool things that I can do. I can just turn on things like contours instead of the contours, hit apply. And if I wanted to, symbolize my map by contours instead of by the filled contours, or the disometric map, however you want to call it, I could. So these contours represent areas of equal precipitation in this case. So everywhere along this circle, precipitation values are the same. Okay, and another way to read an ISO map like this is that as the lines get closer together, those are areas where there's more change occurring rapidly as you travel through space. So it's interesting. What this implies is that, if you're right here and you travel north-south, there's not a whole lot of difference in precipitation change. If you travel east-west, there's a definite gradient as you get more and more precipitation. And you would see that. I see that when I drive out west. The trees get smaller and smaller and sparser and sparser until you get to about right here, and then they're pretty much gone. And you got cactuses and stuff like that. All right. You just have bushes. I'm going to turn the filled contours back on. All right. So I can click anywhere in here, and it'll tell me the value. Okay. I don't know the code. I don't know exactly how the code is operating, but I'm pretty sure, because this is a virtual layer, that as you click the button here, it actually calculates that that interpolation value at that moment. And since it's only calculating one value, it can do that pretty quickly. But again, this is not a layer on disk. It's a virtual layer. Okay, let's go back to the lab here, and now we're going to do kriging using geostatistic methods. And this data set probably be a little bit better than the data set that I brought for class last time. So what we're going to do here is change U.S. Precipitation station, but we're going to change this to precipitation, yearly precipitation. But now we're going to click kriging / co-kriging. Right. And then we'll click next. And here we're going to change this to ordinary kriging. We're going to do ordinary kriging. And with ordinary kriging, there's not really a whole lot of options to choose. We're not going to change any of the defaults. We're not going to include a trend surface in the data. We're going to hit next, and here we get our semi-variogram again. Okay. Here's the semi-variogram, and this is distance. This is the semi-variance. And you could see here that it's selected. Let's see what the the type of the model that it's selected is stable. Okay, so we're right here. I don't like how when this is open you can't. There we go. We selected stable. All right, we're going to experiment by looking at the different models, exponential, Gaussian. We're going to look at the blue line and see which one we think fits the data the best. So we got stable. We're going to experiment with a few others. Spherical. Okay. That one seems to do a pretty good job. Really, the only place where what we want to do is have this line come up, but we want it to kind of more level off about right here, because here we don't really have any additional information. We've got a little bit, because this trend kind of keeps going up even though it gets wider. Let's see what we can do. Circular is probably a little bit better choice. I think exponential is probably the better choice there, because we want this to level off. There might be, let's see, what was stable. Actually, that one looks pretty good, because it's kind of an art here, but we're going right through the center of this data, and eventually it levels off, indicating that there's really no additional interpret. We don't want to use points that are beyond, this would be the range distance. We don't use points there to determine our weights for interpolation. And this seems to be a pretty good fit. I would personally like to see this level off a little bit earlier. I don't know if we can find one that would do that. That one actually looks pretty good. That's leveling off about right. Well, it's leveling off. It's good to experiment a little bit and look at the amount of error that it creates. I'm going to choose that one. Okay, the Gaussian, the normal distribution, basically. All right. To see the blue line describing the variogram, which fits best and which problems do you see? You can also explore the variogram in different directions by clicking on the Show Search Direction. Okay, it's hard to see on mine, but you can expand this, and it says Show Search Direction. If you made this bigger, you could see that as well. But Show Search Direction is the very first option in the view settings. And the reason that you do this is really to see how the semivariance changes according to direction. So if I see that the semivariance changes a lot according to direction, and it really does. So we got in that direction, it looks like it follows that pattern at least a little bit better than it does, let's say, in that direction. That direction, we might want to choose a whole different pattern, and it barely even has a rise. It looks like it's all pretty much unrelated, or there's not a whole lot of variance. Okay, we get more variance in that direction. We see a rise in the variance. So there's a pattern there, whereas there's not much of a pattern here. And if you look at this is precipitation, remember? So in this direction, see these values out here? The reason why we want these to level off is because those aren't really valid values anyway. That's towards the edge of the interpolation. Okay. So same over here. Okay, we're talking about things that are off the edge of the map. This is the United States right here. All right. Okay. So do we see evidence of basically there being anisotropy? In other words, is the variance different in different directions? I would say yes. It's almost certainly the case. Okay, so we look around. You can also increase the bandwidth. I don't know if that is necessary in our case. Okay, I kind of like to keep it small because you can see the differences more abundantly. All right, so we could leave it in a specific direction, but typically what's done is that if you see evidence of that changing a lot, you change this back to false, and then you set the anisotropy value to true, meaning that it's going to calculate a different model in each of the different search directions. Okay, and it shows you all of the models that it's going to calculate, and kind of the search direction that it optimizes for you looks like that. So in other words, going in this direction, the interpolation is going to go further in terms of its weights. It's going to include more and more points that are further away from each other than it will in this direction, in this direction, this way. So that was under anisotropy true. All right, and that one, we don't have a screenshot of that. So would directional semivariograms be better to model the data, and why? We answered that. Okay. Somebody from the coast chimed in there. So yeah, yes. Why? Because the semivariogram pattern changes in different directions. It's not universal. Yep. So I chose Gaussian here. That's not necessarily the choice that you have to make. In practice, I would choose a few different ones and see how I liked the result, but that's what I chose there. Okay. So let's go back. Okay, let's go back to here. So we can click next and finish here, and then we'll be done. So click next. This is the result that it's going to produce. Okay. If we click on any individual point, it'll show us what neighbors it's going to use for those points. Show us the weights at different locations. So here's the weights for all of the points that it chose. So let's look out here where there's less points. So it's choosing points, and notice that it's using this circle to find those points. So we're getting more points in the north-south direction than we do in the east-west direction. Okay. So here, at this point, it doesn't even consider some of these points that are way out in the desert. It doesn't use those neighbors in the interpolation algorithm. It only uses these neighbors that are in the direct area. It does use this neighbor, but let's see what it weights that. What point is that? I can't tell what number that is, but it's one of these two that has a a weight that is about half of what all the other weights are. In fact, in some cases, even lower. Okay, so that's considering all those points and so on. That's considering using all these points. Okay, so let's hit next. And here is here's the result there. Okay. This is predicted versus the measured values. Get some spread out there. Okay. The standard error is something that's good to look at. and then we hit finish. Let's look at our result. I'm going to change the this symbology to match the other one. Okay, so that's our kriging output, and this is our inverse distance weighting output. Okay. There's some fairly significant differences there between those two data sets. So one of the questions just asks, how could you explain the differences between the data sets between these two? Well, the primary thing is that because of the input parameters, kriging chose different weights and weighted points in different directions differently than IDW did, whereas IDW just it only considered the distance to the known locations as the only variable in determining the weights. So the only variable in determining the weights was distance to unknown points. Kriging considered the variance of the nearby points, or actually of all the points, but it used the variance to determine what the weight should be. So if the variance was really high, it didn't use those points as much as variances that were really low to determine those weights. Weighted points with lower variance is higher. So what's the main difference between IDW and kriging? Okay. You may want to create a difference map. How would you create a difference map if you could create a difference map? Or if you can create a difference map, how would you create it? Well, you could export both of your data sets using the same cell size. You'd want to use the same cell size. In practice, a caveat that I should say is, in practice, you probably shouldn't use latitude and longitude as distances. Okay, that's actually a really bad mistake, a horrible thing to do, to use latitude and longitude as distance values, which is what I did. Okay, I'm kind of going off on a sidetrack here, but so this map, the distances are latitude and longitude. So really, the distance from here to here looks really, really long. Okay, but the difference between Seattle and Maine, it looks like it's like 5 times the distance between, Maine and South Florida, when in reality it's probably not even double, although it might be about double. Okay, but because I've used latitude and longitude, and remember, as you get further and further north, the distance between two lines of longitude becomes smaller and smaller. At the North Pole, you can walk all the way around the Earth, all 180 degrees. Maybe like 5 steps, right? If you're on the border between Canada and the United States, it'd still be a pretty far distance, but it would be a lot smaller distance than if you were to walk around the Earth at the equator. Of course, you have to swim part of it too, but see what I'm saying? So that's why this distance appears, what I'm trying to say is this distance appears longer than it should be, and that actually does mess up your interpolation. Okay, but since this was just a laboratory exercise, I didn't change it. You should change this though to some projected coordinate system. Okay, like Lambert conformal conic or something that was meant to be for the United States. Okay, so back to finding the distance. Well, I could export both of these maps and then subtract them from each other using spatial analyst. So if I went, we all know how to do that. Spatial analyst. We're going to go to, you can either do it in raster calculator, or you could just do it, like let's say I could do it in raster calculator. I can't do it right now because like I said, these aren't grids yet. I have to convert them into grids and then do the subtraction problem, press OK. And the result would show me where the big differences occurred. It would show me some of the spatial patterns that occurred in the difference between doing an IDW and a Krieging, and which we did some of that last week. That's why I put that question in there. Okay. Are the reasons for the differences in the interpolation about are the reasons for that? I messed up on that question, didn't I? Are the reasons for that from your knowledge about the interpolation methods? What I meant to ask there is that are the reasons for the differences? It's all part of the same questions. Are the reasons for the differences based in the interpolation methods themselves? Of course they are. Okay, so really you only have to have one answer to this question, but just make sure you cover that the differences between them are because of the differences in the interpolation methods. In fact, if you look at them, you should see differences in areas where IDW did not account for the fact that Krieging, or did not account for the differences in directionality. So here's IDW versus Krieging, and you can see that Krieging did that more, particularly in these areas that are close to the edges. Okay, how does the temperature data set compare to the prediction? So I'm going to let you do the temperature math. Okay. One thing that I didn't cover in the lab that I thought about adding that might be interesting to do really quick is one where we do a co-Krieging, where we put in precipitation, but then we also put in you have to have another data set for it. Oh, that's right. It's kind of a weakness. Maybe it'll let me. Yeah, there we go. Yep. So you have that works. So you have precipitation here. This is not included in the lab, but this is an interesting thing that we're going to do. So we got both of our data sets, and we're going to do co-Krieging. Let's select ordinary again. Okay. And we're looking at semivariance, but this is the semivariance between our points. Yeah, between variable 1, variable 1. We could look at between variable 1 and variable 2. Between variable 2 and variable 2. It doesn't actually look like there's a whole lot of well, there's some degree here, but not a whole lot of semivariance between the two variables. So predicting, using one variable on the other variable, we don't see a big pattern here. These are tighter when we're closer in the distances, and they do spread out, but it doesn't increase at like an increasing rate like we'd expect. I'm just going to click through this.
Which data center are you analyzing?
I'm using, sorry, so I'm using both precipitation and temperature to predict these data sets. So I'm predicting precipitation by using both precipitation and temperature. So it's looking to see if it can explain some of the changes in precipitation by explaining the changes in temperature. This is how you do co-Krieging. And really, we only talked about this a little bit, but I was just going, oops, messed up. Ordinary. And then I really just wanted to look at the results. I'm going to change this to the same parameters that we chose. True. And then hit finish here. See what the result looks like. So here's our co-Krieging prediction map. And it doesn't look a whole lot different than the Kriging prediction map. Yeah, so we didn't add a whole lot. You can see that the semi-variogram between variable 1 and variable 2 didn't really have a rise, so it wasn't really useful to the algorithm. But there are cases where it would be fairly useful to use a different variable to help the predictions. Okay, it didn't change it that much. It did change it some, but not that much. Okay. Sorry about that little tangent there. That was not included in the lab. Okay, so what you have to do is look, you do it again, but just do it for temperature, not for precipitation. Don't do co-Kriging, just do the regular ordinary Kriging again and do it for temperature instead of that. And answer that question there where you said, basically, does temperature have the same or similar patterns when we look at the directional semi-variogram? Okay. You could say it does, it doesn't. It appears like directionality is even more significant, something like that. Okay. All right. Then lastly, what I want you to do is compare the output, this output, to this output. So this is another data set of the United States precipitation. Okay. See that? That's precipitation. This is our data set. You could compare it by subtracting, whatnot. You could just visually compare your results. What can you say about the different distributions? Okay. Why might the spatial pattern in the PRISM data? It's from PRISM. PRISM is the data source. Why might they be more detailed? And again, I don't expect you to have an exact right answer, but think about why it might be more detailed and write something. So what you need to turn in is the answers to your questions, as well as a map of the IDW and Kriging precipitation outputs. One map each. You can put it on the same page if you want, but you can also put it on 2 pages and then turn that in, email that. Anybody have any questions about that? We followed most of the lab through pretty well. This lab doesn't have any models to build, like all the other ones. Most of the other labs did, and will continue to do. But we wanted to explore this other wizard. This wizard is interactive. It doesn't really yield itself or lend itself to automating itself through Model Builder. Still wanted to talk about it. All right. Okay, well, I'm going to go ahead and stop the video, and then I'll let you work on it, turn it in.